What's up guys, Dr. Goodin here to talk to you about the t-test. And in this video, we'll explain what a t-test is and look at 3 different types of t-tests. I'm Dr. Jacob Goodin, Professor of Kinesiology at Point Loma Nazarene University. And in this video, we'll be learning about the t-test for the comparison of 2 different means. Now, there are actually 3 different types of t-tests that we're going to examine in this video, but first, we'll explain what they are and the logic behind a t-test. So let's dive right into it. Now, this information comes from the textbook Statistics and Kinesiology by Drs. Vincent and Weir, and this is from chapter 10. Now, what do we use the t-test for? The test is used to assess differences in means of 2 data sets. And we will compare these 2 different data sets using what's called a t-distribution, which we've seen before when using correlation and bivariate regression. Now, a t-distribution is different from a normal standard distribution because the tails are slightly thicker, and it's best used for smaller sample size that are approximating the population. Now, if we draw 2 samples from the same population and the means of these samples differ by amounts larger than would be expected based on normal distributions, then one of the following conclusions must be true. Either one or both samples were not drawn randomly, but hopefully we've taken care of that in our research design, or some other factor has affected one or both samples, causing them to deviate from the population from which they were originally drawn. And it's this second conclusion that would lead us to reject the null hypothesis and say that yes, these 2 means are in fact different and therefore from different populations. Now, why would we use a t-distribution instead of a z-distribution? Well, using z-scores tends to be inaccurate with small sample sizes, and the t-distributions are similar in shape to the normal distributions, but they have thicker tails. So as I mentioned previously, we use a t-distribution when our sample sizes are smaller. And if you look at a t-distribution, as the degrees of freedom increases, as the sample size increases, it actually does approach a z-distribution or a normal distribution. Now, the t-test was developed by William Seeley Gossett, who wrote under the pseudonym of Student, and therefore this is called the student's t-test. And the student's t-distribution accounts for the bias in estimate of the standard error of the mean when you're using a smaller sample size. So we use a t-table to find a t-ratio that must be reached to reject chance at a given level of confidence. So essentially what you'll do is you will run a series of calculations, which I'll show you here in a minute. You look at the resulting t-statistic that you get, and then you compare it to a t-table to a critical t-value at a certain level of confidence. And if your t-statistic is larger than that critical t-value, then you would say that the null hypothesis is most likely false, and you would reject it and accept the alternative hypothesis. So here's a look at these different distributions. Here is the z-distribution in blue, and you can see that it's much more peaked, whereas a t-distribution with an n close to 30, so sample size around 30, is a little bit more flat. And then a t-distribution with a smaller sample is even flatter still. And so those tails are increasing in thickness as you go from a z-distribution to a t-distribution with a medium sample and then into a smaller sample t-distribution. Now, here is an example of a t-table. Now, if you're looking up a t-table online, some of them have different formats than this, but all of them have these ascending degrees of freedom down the left side. And then across the top, we have corresponding probability or cumulative probability values. So most of the time, when we're dealing with a two-tailed t-test, which we usually will be, we're going to look in this column right here because we want to set our alpha level equal to 0.05. So that gives us just a 5% chance of error. And if we can have lower error than 5%, then we will call that statistically significant. Now, depending on the research design, of course, you could select different alpha levels. Oftentimes 0.01 is also a frequently selected alpha level. So then we scan down this column and match it to our degrees of freedom. So let's say that our sample size was 20, and so we would calculate degrees of freedom as n minus 1, so that would be 19. And if we're looking at an alpha level of 0.05, we just track over, and then we find our critical t value, which is 2.093. And if the t statistic that we calculate with our data is larger than 2.093, then we would reject the null hypothesis. So how do we actually calculate a t statistic? Well, there are different types of t-tests, but they all have the same basic form, and that is a ratio of the mean difference over the standard error of that mean difference. Now remember, previously we've calculated the standard error of the mean, and the standard error of the mean difference is similar. So the numerator reflects the difference between the mean values being compared. So sample 1 versus sample 2, what's the difference in their mean values? And the denominator is the standard error of that difference. So we can think of the t ratio as a signal to noise ratio. The signal is the difference between the means. That's what you're interested in. And the noise is the standard error of mean difference. That's sort of the noise that you're trying to signal out. So the less noise you have in your data set, the less noisy it is, the lower the standard error of the mean difference, the greater your t statistic will be. And likewise, the stronger signal you have, or the larger the mean difference, again, the larger your t statistic will be. Here's an example of what this looks like graphically. The null hypothesis would say that there is actually no difference in the values of x. Okay, in this, there's just one curve here because they're overlaid together. Both of these samples, we would say, according to the null hypothesis, come from the same population. But the alternative hypothesis is that there's actually a difference between these two means, and it is statistically significant such that these two samples actually would come from different populations. And so you can see here under the alternative hypothesis how these two curves are differentiated. Now there are some assumptions that we have to meet before we run a t-test. First of all, the population from which the sample was drawn has to be normal, or at least approximately normal. We need to have our samples drawn randomly, so we can't bias the samples with non-random selection criteria. And we have to ensure homogeneity of variance. Remember that this means that the samples have to have similar variances. Homogeneity means to be the same across the board. So if one sample has a very large variance, meaning a large spread in the data, and the other sample has very small variance, well, then that would violate one of the assumptions for the t-test. The variance of one sample cannot be more than 2 times larger than the other. So there is quite a bit of wiggle room, but more than that, any more than 2 times larger than the other as far as variance goes, and you violate that assumption. Now, there are 3 types of t-tests. As I mentioned earlier, we have the single sample t-test, and this is when you want to compare a single sample against a known population mean. So let's say that you have a group of 10,000 students at your university, and you are interested in whether a group of 30 students who are involved in some sort of accelerated learning program score better on a standardized test. And so you could compare their scores in that sample of 30 to the known population mean from the student body. An independent samples t-test is when you have 2 independent samples and you compare them against each other. Let's say you're comparing strength values between soccer players and basketball players. You have them all do 1 repetition maximum back squats, and then you compare those means. So they're independent samples. And then dependent sample t-tests. This is when you have some sort of a correlated sample. So oftentimes it's when one person is tested pre and post, or under 2 different conditions, and both of those data points come from the same person. So the subject is tested twice. This could be, let's say, before and after an intervention. So maybe you have a group of people who have never weight trained before. They undertake weight training for 12 weeks, and you test their strength levels pre and post, and that would be a t-test, a dependent samples t-test. Now let's go through each of these in turn with examples. So to evaluate a t-statistic from a single sample, this is comparing a sample mean to a known population mean. The t-test for a single sample produces the ratio of the actual mean difference between the sample and the population to the expected mean difference. So in other words, the amount of difference between x and mu that can be expected to occur by chance alone. So this is how we calculate the standard error of the mean, remember, standard deviation, over the square root of the sample. So let's imagine that there is a kinesiology department who is interested in testing out a novel method of teaching the volleyball serve. And for the past several years, they have kept records on all of their students who have taken this volleyball serving test. And it's a test score out of 60, and the average score for all of these students in the past several years is 31. So 31 out of 60 based on the way that they've taught the volleyball serve in the past. But now there's this new method of teaching the serve, and the kinesiology department gives one instructor this new method, and they say, hey, we will compare these scores from your class to the rest of the population at the end of the semester. So the new sample mean, this new class of 30 students, so n equals 30, with the novel methods for learning the volleyball serve, they score a 35 out of 60. The degrees of freedom would be 29 because it's n minus 1. And let's say that the standard deviation was 8.3. So we would calculate the t-statistic as the mean of x, that's the score from the sample, minus the population mean, so that would be 35 minus 31, over the standard error of the mean. And remember, the standard error of the mean is the standard deviation over the square root of the sample size. So that equals 1.52. And we plug 1.52 into our t-statistic calculation, and we get 2.63 for our t-statistic. Now, if we look up in the t-table, the corresponding critical t-value that we need to achieve for statistical significance, let's go to a t-table. We know that our sample size is 30, so our degrees of freedom is going to be 29. And we want to look in this column right here, because our alpha level is at 0.05, and we go across and we find that 2.045 is the critical t-value. Okay, so let's see which one's larger. 0.45, and it appears that our t-statistic is larger than the critical t-value. So this would mean that at the alpha level of 0.05, our result is statistically significant. So this means that there is a statistically significant difference in the scores between the sample of 30 students who learned the volleyball serve in a new, novel way versus the population of students who have been learning the volleyball serve in the old way. So we would conclude then that yes, this new technique is beneficial. Now we can also compute confidence intervals around this mean that we've calculated to see whether or not the population mean falls within our confidence interval. So let's say we desire a 95% confidence interval. So what we do is we use this equation right here. Confidence interval equals the mean in x plus or minus the critical t-value times the standard error of the mean. So really the only two things that we need for this are the mean of x and the standard error of the mean, both of which we've already calculated. So we see that it is 35 plus or minus 2.045, which was our critical t-value, times 1.52, which comes out to 31.89 up to 38.11. And so what this says is that we are 95% confident that the true mean of this group of 30 students, if you tested 30 students over and over and over again with this new serving method, we're 95% confident that the true mean would be somewhere between 31.89 and 38.11. And because both of these numbers, this entire range, is greater than the previous mean of the population of 31, we can reject the null hypothesis. Okay, so that was comparing one sample to a population, or a one sample t-test. Now we're going to compare two independent samples. This is called an independent samples t-test, and it tests whether two samples were drawn from the same population or whether they are drawn from different populations. And usually this will involve two different groups of people. So in this example, we will consider an athletic trainer who's comparing two different ankle sprain treatments on ankle swelling. And to measure ankle swelling, we will compare ankle volume in milliliters between patients who get standard care and patients who get the new treatment. So this athletic trainer would gather two different groups of people, sprain all of their ankles, treat one group in the standard way and one group in the new way, and measure ankle swelling before and after those treatments just to see if there was a difference. So in this case, we are going to use the standard error of the difference, not the standard error of the mean. So let's take a look at the data, and we see that we have 15 individuals in both groups. Standard treatment is on the left, new treatment is on the right, and we're comparing these values of milliliters of ankle swelling. Looks like the standard error of the difference is 0.836, and we calculate the standard error of the difference similarly to how we calculate the standard error of the mean, but in this case we have to factor in the standard deviation and the group size from both of these groups. Now, to calculate the t-statistic, we will look at the difference in means over the standard error of that difference. And in this case, it's 2.15. Is that t-statistic greater than the critical t-value? To answer that question, first we need to figure out how many degrees of freedom that we have. Now, when you have a two-sample t-test or an independent samples t-test, we calculate degrees of freedom slightly differently. It's not just n minus 1, it's the n of one group minus 1 plus the n of the second group minus 1. So in this case, the total would be 28 degrees of freedom. So you're subtracting 1 degree of freedom for each group in this case. And so instead of 29 degrees of freedom, you have 28. So let's take a look at the critical t-value at 28 degrees of freedom for 0.05 alpha level, and that's going to be 2.048. So let's see if we met that. Our calculated t was 2.15, and this is in fact greater than 2.08, so we actually reject the null hypothesis. So because we rejected the null hypothesis that there's no difference between groups and accepted the alternative that there was a difference between groups, does this mean that the new treatment caused less ankle swelling? Well, the t-statistic, and this is important, the t-statistic does not identify the causative factor. Rather, we need careful controls and proper experimental design in order to identify the causative factor. Only if the control group is closely monitored, to ensure that only chance operates on it, and if only one independent variable is permitted to influence the experimental group, then the independent variable may be identified as a causative factor. So what this is saying is that you have to carefully control all other aspects of the experiment. Perhaps the group that received the new treatment for the ankle swelling, maybe they were also doing some other things with their diet, maybe taking anti-inflammatory drugs, or maybe eating an anti-inflammatory diet, or maybe they were also elevating their legs at night when they slept and the other group wasn't doing that. So we have to make sure that we control for all those things. The statistical analysis only quantifies the association between the independent variable and the dependent variable. It doesn't tell you exactly what the cause was. So in this case, how would we calculate a confidence interval? Well, we need a confidence interval around the change in x, or the difference in x, rather. So the critical t for a two-tailed test at 0.05 with 28 degrees of freedom, as we looked at before, is 2.048. So we calculate the difference in means, that would be 41.53 minus 39.73, and then we add and subtract the critical t-value multiplied by the standard error of the difference. So in this case, the 95% confidence interval says that there is a 0.09 to 3.5 milliliter difference between the two treatments. And what we can say then is that since this 95% confidence interval excludes 0, we would infer that the two samples represent different populations and are 95% confident that the true mean difference between those populations is somewhere between 0.09 and 3.5 milliliters. Now, if we wanted to do the same thing for 99% confidence interval, we'd have to go back to the t-table, and instead of looking at the 0.05 level, we go over to the next column, or the next couple columns over to the 0.01 alpha level, and then we go down and find the critical t-statistic there, and it would lead to a wider confidence interval, because now we want to be 99% confident, not just 95% confident. Now, it's important to note, if you have unequal sample sizes, the calculation does change. It gets super complex, as you can see here, and most of the time you'll be doing these t-tests using a stats program like Excel or SPSS or JASP or MATLAB or R. So personally, I don't have my students memorize this, nor do I have it memorized, but this is what it looks like, and you can see that we have to account for the two different sample sizes in this equation. If we simplify this down, if we assume that n's are equal, in the case that we do have equal n between the two samples, then we get our now familiar standard error of the difference. Okay, so what about a repeated measures t-test or a paired subjects t-test? We use these when we test subjects more than once. So this could be pre-test versus post-test comparison, or one treatment versus another treatment, or one condition versus another condition in the same subjects. Now with these dependent samples, we assume that a correlation exists between a subject's pre-test and post-test. For instance, high scorers on a pre-test would probably be high scorers on a post-test, and vice versa. Now because these scores are correlated, the Pearson R correlation coefficient, or R, will factor into the standard error of the differences. And you can see here in this equation, this 2R, and because we're subtracting this chunk of the equation, the larger that R is, the smaller that the standard error of the difference will be. So this means that the greater the correlation between the pre-test and the post-test scores, the smaller the standard error of the difference will be. So let's look at an example. Table 10.2 is looking at the effects of a 4-day bicycle tour on self-esteem. So here we have the pretest, the self-esteem pretest, 38.4, that's the mean. And then the post-test, it looks like it went up a little bit, but our question is, was this statistically significant at an alpha level of 0.05 or 0.01? We have the standard deviations, standard error of the means, and then here we have the standard error of the mean difference already calculated with a very high R, 0.92, so a high correlation, and then the t-statistic of negative 6.22. So here's how we perform those calculations. Remember that we need to calculate the standard error of the difference, and that takes into account standard error of the mean 1 and mean 2. So we plug those in to the equation, and we get standard error of the difference being 0.37. Then to calculate the t-statistic, we take the difference in mean, so that's going to be 38.4 minus 40.7, and underneath that we put that standard error of the difference that we already calculated, and it comes out to negative 0.622. Now in this case, for dependent samples t-tests or paired samples t-tests, the degrees of freedom calculation is not the same as the independent samples t-test. We have one extra degree of freedom. So instead of subtracting 1 degree of freedom per group, essentially it's the same group. So we have 44 degrees of freedom if our starting sample was 45. So we won't look at a t-table, but if you did look up on a t-table, you would find that the critical t-value at an alpha level of 0.05 is 2.015, and the critical t-value at an alpha level of 0.01 is 2.692. So is there a significant difference here between the pre and the post test? Well, our t-value is negative 0.622, and what we can do is actually effectively ignore that sign. We just take the absolute value of it. Remember, this is a two-tailed t-test, so we're looking for whether it's larger or smaller, and a t-distribution is symmetrical. So a t-table is only going to show you the positive side of that curve. So we can, in this case, effectively reject the null hypothesis. We can also calculate a paired sample's t-statistic using the difference in scores over the standard error of the difference. And recall that this is the standard error of the difference, so if we put this standard deviation over square root of n underneath the mean difference score, then we can get the t-statistic. So here's a second paired samples t-test example. This is 10 weeks of training and how that affects VO2 max. So we have all of the pre-test scores here and then the post-test scores here with the difference in those scores over here. Notice that most of these scores are positive. Here's the only negative score. So we can probably assume that this will be a statistically significant difference, but let's see just in case. So the degrees of freedom here is only 7, which means we will need a larger t-statistic for this to be statistically significant. we can calculate t as the mean difference. So here is the mean of the pre-tests, and here is the mean of the post-tests. The mean difference is 3.4, and it looks like a little bit of rounding error here, but we put 3.3, should be 3.4. Regardless, we put that over the standard error of the mean difference, which is a standard deviation over square root of n. And we solve that and get 2.5. So what is the critical t-value at 0.05? Let's look again. Degrees of freedom is 7. We go over to 0.05 and it looks like it's 2.365. 2.365 is smaller than 2.5. So in this case, it does appear that the training worked. At the alpha level of 0.05, we can say that there is a statistically significant difference between the pre-test values and the post-test values after 10 weeks of training. Now let's calculate the confidence interval. Remember that we take the difference in means plus or minus the critical t-value times the standard error of the difference. And we would get between 0.2 to 6.4 milliliters per kilogram per minute. And so we can say that we are 95% confident that the true mean difference in VO2 max is somewhere between 0.2 and 6.4 milliliters per kilogram per minute. The null value of 0 is outside of that confidence interval, so it appears that the training has worked. Now, the last thing to talk about regarding t-tests is the magnitude of difference. We've talked about whether or not there is a statistically significant difference as determined by the t-statistic and comparing it to the critical t-value. But how big is that difference, and is it meaningful or not? And we call this the size of effect, or the magnitude of difference. Just because an effect is statistically significant does not necessarily mean that it is big or important. If the values of n are large enough, and if standard deviations are small enough, especially if the design is repeated measures, so paired samples t-test, then statistically significant values may be found between means that are quite close together. So a practical explanation for this is that if you have a huge sample size, there could be a very, very small difference between the two samples, and you can find a statistically significant result. But it might be that that difference is not meaningful. It's not large enough to be actually practical. Sometimes we call this clinical significance. So omega squared is one statistic we can calculate that estimates the percentage of variance that can be explained by the influence of the independent variable. This is analogous to R squared. We calculate omega squared as t squared minus 1 over t squared plus both of the sample sizes minus 1. From our previous ankle swelling example, if we calculated omega squared, we could say that 11% of the variance in ankle swelling is due to the treatment received. So not a huge amount of the variance, but enough to be possibly significant. If you're an athlete, 11% could mean, 1 day less of swelling and 1 day sooner back to practice, and that is enough to be meaningful. We can also calculate effect size. Effect size is similar to a z-score in that it's standardized, and from the ankle swelling example, we would calculate effect size as the mean difference over the standard deviation of the control. So the difference between treatments was 0.72 in the ankle swelling example, because if we take the mean from one group minus the mean from the other group over the standard deviation, we get 0.72. So we can say that the group who received the new form of treatment had 0.72 standard deviations less ankle swelling than the group who received standard treatment. Whew. All right, guys, that was a long one, all about t-tests. We introduced the concepts of t-tests, what they are, the logic behind them, what a t-statistic is, how to use a t-table, and we looked at examples of 3 different types of t-tests: the single sample t-test, an independent samples t-test, and a paired samples t-test. Now, if you had any questions about that, let me know down in the comments below. I'll be creating videos soon showing you how to do t-tests in Excel and in SPSS, and eventually I'll do the same thing for JASP, so stay tuned for those. And as always, I'll see you guys on the next video. And I'm just kidding, they wouldn't sprain their ankles, they would take